Good morning, everyone. This is Jim Chastain with EasyPower. Welcome to the EasyPower Refresher Tuesday webinar series. Today we're looking at current limiting fuses and how EasyPower deals with them and calculates arc flash results. And we appreciate your attendance today. And as we are most likely to do, we'll be running a poll question here shortly. Today's agenda is to briefly cover the background in arc flash research as it evolved with respect to current limiting fuses and how or the model that was developed as a result. Talk about some of the changes that have occurred with the advent or the release of the 2018 version of 1584. And then again, talk about EasyPower's implementation. And a spoiler alert, what I'm doing is not really an EasyPower recommendation as far as the technology or the current limiting fuses. I'm really responding to a number of questions that we get from time to time regarding the topic and sharing with you how the model is implemented, and then it's up to you to. I'll explain more of that when we get to the tail end, so it'll make a little bit more sense, hopefully, by the time we get there. Meanwhile, let's run our poll questions, and again, appreciate your participation and your feedback. Obviously, there's no obligation. I do appreciate your attendance today. So let's give this another 5 seconds to get a quorum. All right, looks like we have enough people have voted. Here's how it came down as far as the voting. Thank you. And then secondly, do you use or have you considered using current limiting fuses for arc flash energy reduction or mitigation? And kind of the corollary to the question is, how did you implement it? And did you have an issue with EasyPower tools, which is where I'm going with this conversation. So it looks like we kind of have a quorum, and let's share this. So sure enough, the audience that's attending has a relative reason for attending and answering the question. So again, thank you for attending today, and let's kind of jump into this. So when IEEE 1584 2002 was released, one of the things that we learned as a result of the battery of testing that they did is that they defined several terms that, while they may have been understood, the purpose was to better define the correlation between things like bolted fault current and available fault current to the subject of arc flash characterization. And so in the process of doing the testing, they realized that the arcing current was going to be something less than the maximum bolted fault current, which had been well understood in terms of the need to calculate it and determine whether the system could withstand the surge. But the arcing fault current was a little bit more difficult to get a specific value on because it involved the thermal properties of the electrical plasma, and there are several other errors or correction factors that came into play, including size of the enclosure, air gap, and even other parameters that weren't necessarily able to measure at the time. So the point came up, or the bottom line was, it was difficult to predict what the arcing currents were going to be. And so the solution that was evolved as far as 2002 was to calculate the worst case arc current and then also calculate the clearing time at whatever protective device was being used at 85% of that predicted arcing current. And then the recommendation was to take the incident energy which resulted, that was the most conservative value. And sometimes that would be the 85% value, and sometimes it would be 100%. Now at the time, in 2002, it was left up to the person doing the analysis to determine what that difference was, whether it was 85% or 90% or 72%, whatever the difference between the worst case and the reduced arcing current was left up to the engineer doing the study. Well, with the advent of things like current limiting fuses, that difficulty in predicting arcing current presented a problem when we try to apply the technology of current limiting fuses. And so at the time, the fuse manufacturers had come up with what they call let-through energy that was more a function of a defined time and the fact that the current, the fault current, the arcing fault current or the bolted fault current, whatever it was high enough that it basically instantly cleared the fuse, or allowed the fuse to clear the arc in as little as a quarter of a second. But even that time was variable based upon when the fault occurred as far as the voltage waveform. And so there was an effort to include the current limiting fuse model, or develop a model, at the 2002 standard test battery that was applied or recommended when arc flash incident energy was based on the bolted fault current and then the class of fuse that was being used. And so there's several limitations. So this is an excerpt from 1584. This is actually the 2018 version, but the verbiage is pretty much the same that was included in 2002. And what we find is that they had several limitations. First of all, they only apply to systems that have electrode configuration, and these are because of this is what was used in the test battery, and it's unclear of how far out afield the results would lie because the tests weren't done with other, for instance, electrode configurations. So it's only applied to electrode configurations vertical in a closed box. It only applies, this model only applies to classes L and RK fuses. And it's only applicable to low voltage where the fault current is very high compared to the minimum fault current required for limiting the current. Now again, all of this is, you have to go to the data sheets for the fuses themselves or to the charts that the manufacturer provide on the data sheets. And what we have is a set of, or an equation that predicts the current limiting fuse calculations based upon testing performed in the smallest enclosure size. And with that admonition, the recommendation is to use that as your calculation basis, because larger enclosure sizes would be less conservative. So again, there is somewhat of an attempt to kind of be specific and yet cover a worst case scenario. Now, as far as notes on this, or what this meant, is that the standard 1584 is the result of curve fitting to match the data that was taken. And pretty much the same is true regarding the current limiting fuse equations, but it's significant that no additional testing was done between 2002 and 2018 on current limiting fuses. The verbiage describes that the clearing time was so quick it was difficult to get test results that were consistent or predictable outside of the range that had already been done. And so the results could differ based upon the system voltage, the closing angle of the voltage wave, and obviously the distance from the arc. So the bottom line is the model that we have is only applicable to low voltage systems, and these values of current limiting fuses in class L and RK1. And so this is the equation itself. And as you can see, although it may be tiny, small font, it's based upon correction factors and the voltage fault current. And these correction factors are derived from the range of fault current from this chart below. So what it amounts to is based upon the current that you have, you use that particular correction factor for that insertion in the equation, and this will give you the energy calculation. And so it's a fairly complex arrangement, and that's part of the reason why I suggest you don't necessarily deal with it on your own, but it's easy to see how EasyPower applies them. So if I just pick out a couple of these fuses, for instance, a 350 amp RK1 with a lower limit between 3.16 and 5,000 amps, these are the correction factors that are applied. And this again is the equation down at the bottom. And what I'm going to do is jump into EasyPower and show how that gives us some results. So let me jump into the 350 amp version. Now, the main thing I want to show here is how to implement the feature. So we've got our one-line diagram. I've set up several different loads and several different current ranges. This is below the current limiting range for this particular size fuse. And so I would expect that the equation will not be applied to this particular branch. So if we look at the short circuit current and then fault all the buses and look at the current, we can see that we have 3,000, 5,000, 18,000, and 64,000. Now, the short circuit options, arc flash hazard tab, currently I'm using 2018 version, momentary current. If I go to the advanced tab, I can apply or not apply the current limiting fuse equations. So I'm going to start with having them not apply and hopefully be able to see the change when we look at the applying the current limiting fuse equations. All right, so again, these are relatively civil instant energy ranging from, well, 14 joules up to 3.8 joules. I wouldn't call that civil in all cases, but this again is without the current limiting fuses. If I go into short circuit options, advanced, apply current limiting fuses, and then go back and apply them, it's difficult to see, but these actually go down on some of the currents. So what I've done is use my scenario manager. I'm going to go back to database, go to the scenario manager, and show that I've created with the equations applied and without equations applied, and I'm going to compare the two. So let's go ahead and do that. And we're going to compare fuse equations. Now the reason I said that EasyPower doesn't necessarily recommend this, so we see on the below the range which was the lower one, it didn't change because the current limiting fuse equations do not apply. On the other three, I get different values, or worse or better, the worst case indicated by the X. So without is indicated worse for very high, with equations is indicated worse for mid-upper, and without for mid-low. Again, my definition of the different scale of or value of the current. I'm going to close this and do the same thing. So this basically is my point. It doesn't necessarily give you lower values based upon, and it's difficult to estimate what the results will be just looking at the current. I'm going to go back and do this to 650 amp. I've got the same kind of a situation, and in my scenarios, I've got both with and without fuse equations. So let's go ahead and create a report comparing the two. Now again, all I'm trying to do is make sure you know how to invoke the CL current limiting equation, apply the current limiting equations. And then if you want, make a comparison report. And again, on the low range, things don't change. But on the upper ranges, in this case, the lowest one was worst case, and the upper values were best case. So where does that leave us? Well, my point for kind of, and I don't mean to disparage this at all. I'm just basically saying, as a general rule, you cannot count on current limiting fuses to give you the most conservative result or even the lowest incident energy. You need to really take a closer look, and the reason I kind of downplay this, or have, and I see the industry downplaying it, is that when I was going through the standards trying to come up with this information for the presentation, I noticed in the 2002 version of 1584 a typo between the label on the figures that was being used and the actual class. In this case, they have the chart labeled class L800, but the figure is labeled class RK800. Turns out the R is only rated up to 600 amps, and L goes from 600 to 6,000. So they've kind of crossed their tips on conveying this information on at least these two charts. What's significant to me is that the typo showed up in the 2002 version, but it was repeated, the same display or the same representation was displayed in the 2018 version, as this discussion on current limiting fuses was moved from the main body to the annexes in 1584-2018, which in my mind suggests that this is not often used in industry or prioritized, and so there is not that much attention being paid. Nevertheless, by all means, I'm open to other questions on how to use the tool to apply it, and it's not up to me to worry about whether or not I'm getting the best answer. Hopefully that was a cogent discussion of what's going on. Thank you for attending today. Certainly we have some very informative webinars coming up. You need to check the website. And thank you for attending, and you're welcome to contact me or tech support if you have any additional questions. Have a good day.